Hi, my name is Ritwik Gupta, and I'd like to talk to you about our work today titled xView3-SAR, a massive data set for detecting dark fishing activity using synthetic aperture radar imagery. This work was done in conjunction with the Defense Innovation Unit, the Global Fishing Watch, the U.S. Coast Guard, NOAA, and the National Maritime Intelligence Organization. Illegal, unregulated, and unreported fishing is a massive problem all around the world. It's estimated that 1 in 5 fish caught around the world originate from IUU fishing. Think about that. 20% of the catch that you eat, 20% of the fish that you've ever consumed in your life is coming from completely unverified, unvetted, and potentially unsafe sources. And illegal fishing is a huge problem for many reasons beyond eating unsafe fish. Almost all life on land depends on life in the water. And it's estimated by the U.S. Coast Guard that 93% of the world's major marine fish stocks are classified as fully exploited, overexploited, or significantly depleted. That's crazy. If we can't sustain our marine biospheres, we are sure to lose our land biospheres as well. One of the reasons that IUU fishing is exacerbated, and one of the main mechanisms by which it is conducted, are these things called distance water fishing fleets. These distance water fishing fleets overfish in other countries' exclusive economic zones, which devastates their global economies. And an excellent example is Somalia, where these distance water fishing fleets completely destroy marine ecosystems off the coast of Somalia, making these local fishermen rely on other means of income, such as piracy, to sustain their operations, right? To feed their families. And not only does this devastate global economies, this also introduces poorly regulated catch into the global supply. Some of the biggest countries responsible for distance water fishing fleets are China, Taiwan, and Spain. And so understanding where these distance water fishing fleets are, where IUU fishing is happening, is critical to protecting life on this entire planet. If you are a commercial operation, if you're a fishing operation, if you're carrying passengers, if you're over 300 gross tonnage, there's a whole list of criteria that you might fall under. The International Maritime Organization and many countries require you to be outfitted with what's known as an Automatic Identification System beacon, an AIS beacon. And what an AIS beacon does is it broadcasts your GPS location and information about your vessel periodically. For example, your registration, where you came from, and interesting things about your ship such as its size, and even, for example, your speed. The thing is that if you're conducting illegal operations or operations that you don't want the world to be aware of, it's very easy to turn that AIS beacon off. And once that beacon is off, you are now a small vessel on the world's largest environment. It's the hardest finding a needle in a haystack problem that you can imagine. You're a 30-meter vessel on an object that is hundreds of millions of square kilometers large. Luckily, we have a form of imaging known as synthetic aperture radar, which provides us an all-weather source of surveillance in either the day or the night, which makes it possible for us to illuminate illegal fishing vessels in any time of the day in any sort of weather condition. On the bottom right is an example, is actually a coverage map of an open source satellite constellation called Sentinel-1, which is a synthetic aperture radar constellation, and all the areas that are in red are areas which the Sentinel-1 constellation visits very frequently, and all the areas in blue are where it visits infrequently, infrequently being maybe once every 7 days. This map has changed over time. This map is a bit outdated as we've added more and more ocean areas to this map. But just to give you an idea of, we're able to cover a lot of really interesting areas and a lot of areas which are severely impacted by illegal fishing. For example, the Bering Strait, off the coast of Iceland, as well as off the coast of the Gulf of Mexico. So what is synthetic aperture radar? You might be wondering, I've mentioned a few times now. I'm sure all of you are familiar with electro-optical imagery, satellite imagery as we like to call it. You've all opened Google Maps, you've all opened Google Earth and looked at your own house. And electro-optical imagery is a passive mode of sensing. It works exactly like it's been described to you in your high school physics classes, right? There is an external light source, like these fluorescent lights in this room, the sun, and they're beaming photons down towards the Earth. These photons are absorbed and re-emitted by objects in wavelengths that they don't like, right? They're rejecting wavelengths that they don't want to, that they fundamentally do not agree with, in very layman terms. And those wavelengths, right, that our eyes then pick up, or our camera then picks up, are what we perceive as color and brightness and all sorts of other things. The issue is that objects that we want to monitor are not the only thing that like to reflect photons. Things like clouds and smoke and haze also reflect photons, and that's where we're able to see clouds in satellite imagery. And the thing is that 2/3 of the world at any given moment in time is covered by clouds. That's just how things are. And so if we were to try to use electro-optical satellites, like the ones that Google Earth uses from Maxar and Planet and other sources, we'd be missing most of the world's activity at any given moment in time. What synthetic aperture radar imagery does is it takes a satellite, or a plane, in this case we're going to focus on satellites, and it beams polarized microwaves down to the Earth. These microwaves interact with objects based on the object's fundamental dielectric properties. They bounce around, they scatter all over the place, they interfere with each other, and they make their way back to the sensor. And the greater distance that we can integrate these returns over, the better resolution that we can resolve on the ground. And that distance that we're integrating over is the synthetic aperture in the synthetic aperture radar. Here's an example of the difference between an electro-optical image and a synthetic aperture radar image. On the left is an image that I took from Google Earth. The underlying data provider is Maxar, Worldview 2 Imagery. And you can see very clearly with your own eyes that that is clearly some sort of suburban neighborhood, some sort of school or mall on the bottom left there. There's trees, there's roads. You can even identify the colors of different roofs, and even identify different types of material used to build those roofs. I've cut that image in half diagonally. And that same exact neighborhood is portrayed on the right side with synthetic aperture radar. And now you can see a few different things, right? There's no color, it's this eerie black and white image. The same features that you can discriminate in the electro-optical image are no longer very easy to discriminate in synthetic aperture radar. There's these bright white patches that don't exist over here. And what you're seeing is, on the left, you're observing the intensity of the return in red, green, and blue wavelengths that are composited together to make this image. So how bright was the red return, how bright was the green return, how bright was the blue return. And what you're observing on the right in a synthetic aperture radar image is how reflective was that point on the ground with respect to the microwave that was broadcast down to it. Right? So these edges were more reflective than the things that are appearing darker. You might even notice some effects such as this building, I'm telling you it's a tall building, which appears diagonal, whereas all these other buildings in the electro-optical image appear to be completely imaged from the top down. We'll get into that in a second. But just to visually quantify this, or visually qualify this for you, synthetic aperture radar imagery looks completely different than electro-optical imagery, requires specially trained analysts to interpret it, and as you can imagine, all the automated methods we've built to interpret electro-optical imagery over the years will not work with synthetic aperture radar imagery, at least not out of the box. And so that's what we wanted to focus on. The computer vision community at large does not work with synthetic aperture radar imagery. We are very familiar with RGB imagery, electro-optical imagery, and we wanted the world to work on synthetic aperture radar imagery to solve this problem of detecting dark vessels conducting illegal, unreported, and unregulated fishing. And so what we did was we collected a massive data set, over 82 million square kilometers of synthetic aperture radar imagery, and labeled it with over 243,000 annotations of objects, right? Are these objects, for example, wind farms out in the oceans? Are they oil rigs? Are they vessels? If they are vessels, are they fishing or non-fishing vessels? And regardless of the type of object it is, what's the length of that object, right? Is it 100 meters? Is it 50 meters? And with what confidence do we believe all these attributes to be true? Because the way that we derive these labels is using an automated algorithm which takes an ASB ping at one point in time and projects it out to the time at which that synthetic aperture radar image was taken. So by following this process, including automated and manual labeling, we built this massive data set called xView3 that we're releasing out to the world. In addition to synthetic aperture radar imagery, we also, for every single scene, give you additional context. So we give you the wind direction for that scene, right? So which way was the wind blowing for that exact image that was taken at that time? What was the bathymetry, right? The depth of the water for that time, which helps you contextualize fishing vessels, for example. They might not be fishing in certain areas versus others. We give you things like the wind speed, right? All things that might help you contextualize that image further and the activity on that image further as well for you to train your machine learning models on. And here's what the data looks like. As I mentioned, we're measuring reflectivity. So you can imagine these large metal buckets, which is what a ship is essentially, out on the water, come off as these extremely bright patches against the completely non-reflective surface that is the ocean, right? So we have everything from boats waiting off a shore to dock into a port. We have wind farms in these nice gridded patterns. We have ships emitting some sort of biological or organic matter, which is causing this super dark pattern on the surface of the ocean. We even have radar interference patterns, which are other sort of C-band microwave sort of antennas that are operating in that area, which are interfering with the imaging of the satellite itself. So this data set is huge, it's diverse, it's very interesting, and the whole idea is that taking all this data, can you start telling us different characteristics about the vessels and objects in the scene. I'll get to that in a second here as well. So again, we're giving you 991 scenes. These scenes are massive, over 29,000 by 24,000 pixels large per scene. All the geospatial work has been done for, right? So we've done all the hard geospatial work. All these scenes have been projected to the UTM coordinate reference system. We've reprojected them to be square pixels that are each 10 meters large. And we've partitioned them into 4 sets for you to be able to train your machine learning algorithms on. And on the bottom right here shows the geographic distribution of where those scenes come from. So you can see off the coast of Finland and Sweden, off the coast of Spain and France, where there's a lot of illegal fishing activity, off the coast of the Gulf of Guinea, and some other regions around the world as well. And the things, right, the metrics that we are judging you against are here. 5 different metrics. How well can you detect an object? Doesn't matter what the object is, how well can you detect an object on the image? If the object is close to the shore, where we see increased artifacts in synthetic aperture radar imagery, how well can you detect objects that are close to the shore? We define that as within 2 kilometers of a shoreline. How well can you take an object and classify that as a vessel and not a vessel? If that object is a vessel, how well can you classify that object as a fishing vessel or not a fishing vessel? And lastly, how well can you quantify the length of that vessel in terms of meters, right? And we score that on a percentage error. We give you prize money to participate in this challenge, right? So if you get first place and you open source your models, you can win $52,000, and the prize money then decreases for a total prize pool of about $250,000, which we think is a pretty good incentive for the community to work with, not only in terms of data size, but now also in terms of monetary incentive. Some of the open research problems that we want people to tackle with this data set are contextual learning. One of the most common things we do in the field of machine learning today, especially when we're dealing with large images, is we cut those images into small tiles, right? We'll take a massive image, let's say that's 1024 by 1024, and we'll cut it up into small tiles that are 256 by 256 each. And each of those tiles is then fed into a model independently, trained upon, and also inferred upon, with no sort of relation to any other chip out in the world. In fact, we randomly shuffle these chips so the models are able to do a better job of training on them. But the thing is that chipping imagery removes relevant context over large distances. Feasibly, some sort of activity in this chip and the activity in this chip should be much more closely related than activity in this chip and this chip out over here. So, given that we're giving you these scenes that are 29,000 by 24,000 pixels large, on par with some of the largest digital pathology slides that we can work with, and 10,000 times larger than ImageNet, which is one of the machine learning benchmarks that we work with, how can you incorporate long-range geospatial information when making these predictions? We really care about representation learning. An electro-optical image generally has one representation, right? If you take an image, that's what you get. The wavelength returns and intensities that you get are what you see on the screen. That's not exactly true for synthetic aperture radar imagery. For synthetic aperture radar imagery, we're dealing with an entirely different data space. All electro-optical images that we deal with are real valued. They range from 0 to 255 in terms of their pixel values, or 0 to 65,536 if they're 16-bit images. Synthetic aperture radar images, at their core, are complex value data. Not only do they contain an amplitude, which is what you're seeing on the screen here, but they also contain phase information. And that phase information gives us a proto-depth sort of cue, which is not available in electro-optical imaging. And so how do you properly handle complex value data when modeling synthetic aperture radar imagery is also of interest to us? In addition, as I mentioned, these microwaves that we're using for synthetic aperture radar are polarized. You can broadcast vertically polarized radar and then receive vertically polarized radar. Vice versa, you can also broadcast vertically polarized radar and receive horizontally polarized radar. You can also, so that's called VV and VH. You can do the same thing for HH and HV. So for a single spot on the ground, for a single image, there's not one valid representation, there's 4 different valid representations at the same exact time. This is the same exact scene with images captured at the same exact time, except we're measuring different polarizations. And you can see they look drastically different. What's more interesting is the geometry of the SAR sensor starts making a difference. If I were to tilt a satellite sensor by 1 degree or 2 degrees on an electro-optical sensor, what you'd start seeing is maybe the size of buildings a little bit, right? You'll be able to see the side of a building by 1 degree or 2 degrees. In synthetic aperture radar, you're now changing the fundamental behavior of the ray tracing because the angles at which those waves interact with the objects has now changed. They will bounce differently, they'll interact with objects differently, and they'll make their way back to the sensor differently. So by changing the geometry of the sensor, you'll get an entirely different image, which may not look the same as the image captured before, in some sort of meaningful way. So representation learning for synthetic aperture radar imagery is a big unsolved problem, especially when you want to do representation learning efficiently. And one more thing that we want people to work with with xView3 is this problem of efficient inference. Ideally, we want these models to be running on a Coast Guard cutter so that we're removing all the latency associated with downlinking an image, running inference and broadcasting it out to a Coast Guard ship, who are operating in very, very low network settings. We want the Coast Guard cutter to directly interface with a satellite, download the image, run the assessment, and immediately within 15 minutes know exactly which vessels to target within the area that they're operating. So to this end, we don't want you to just make machine learning models that work well. We want you to build machine learning models that work well and can run efficiently on constrained computational hardware so that can fit on a Coast Guard cutter. In this case, we want you to run an assessment on one scene in 15 minutes on a machine with a 1 Tesla V100, 60 gigabytes of RAM, and 8 vCPUs. That's still a pretty beefy machine, but that's still a very constrained target when it comes to modern day deep learning. In the months since we've run this challenge, because xView3 is now over at the time that we're giving this talk, we've actually taken the winning models and made them even better. We've productionized them, we've made them further efficient, and we've retrained them to be a little bit more better in the context that we care about. And we deployed them in a platform called C-Vision, which is operated by the Department of Transportation and the Department of the Navy. And what you're seeing on the screen here is a whole bunch of circles, red circles and yellow circles. Every single circle that you see on the screen is a detection that our algorithms made on synthetic aperture radar. If the circle is in yellow, it means that we're able to make a detection. We can see that there on the left. That's the vessel that we detected. We thought that vessel was 29 meters in length, and down there we thought that it was a fishing vessel. That vessel was a broadcasting AIS. We were able to correlate that detection to a known AIS ping at the same location and at the same time within some sort of small delta. And so that detection was correlated to the Zhongshui 757, which is registered as a 40-meter length vessel, and if you were to click on that registration, it actually does come up as a fishing vessel. What's more interesting is all the dots that you see in red. Every single dot you see in red is a vessel that we detected that was not broadcasting AIS, that we were not able to correlate to a known ping or a known location. And so here's a vessel that we picked at random. Again, you can clearly verify with your eyes that that is clearly a vessel. We think that's a 60-meter length vessel that is a non-fishing vessel. And you can see we're picking up orders of more magnitude dark vessels than we are picking up lit vessels, right? So we're able to now start characterizing activity on the ocean, especially illegal, unreported, and unregulated fishing activity, as well as activities such as drug smuggling, human trafficking, instances of illegal transshipment that violate sanctions using xView3. And using xView3, we've actually been able to help law enforcement agencies such as the Coast Guard. They're not law enforcing, they're just enforcing certain exclusive economic zones to help better patrol the oceans. That's xView3-SAR. For further details, all the models, all the data, everything about this challenge is entirely open source. You can download that at the QR code below. And for further questions, please refer to our full paper, which was presented at the NeurIPS 2022 conference. Thank you.